Welcome to today's lesson. We are going to look at determination of the focal length of a convex lens. Method 1, we are using focusing a distance object. We have the apparatus needed. We have meter rule, lens, a lens holder, and a screen. We are going to arrange the apparatus as shown in the diagram. We have the screen, we have the lens and the lens holder, and we have the meter rule. So we are using the idea that the parallel rays from a distant object are always brought to focus on the principal focus, as we have seen previously in our lesson. Now, you're supposed to adjust this lens until you get a clear image on the screen. Remember, we are saying that rays that are parallel and they are coming far away from the lens, they are brought to focus on the principal focus, which implies where we have the image is the principal focus, and therefore the distance between the screen and the lens will give us the focal length. That's what you're supposed to measure. Measure the distance between the lens and the screen, and you're going to get the focal length in centimeters. Then we move to the second method. We are using illuminated object and a plane mirror. Again, we have the apparatus as meter rule, lens, a lens holder, and a screen. And we are going to arrange the apparatus as shown. We have the mirror, where we are attaching, or we are fixing our mirror using the plasticine. We have the lens on the lens holder. Then we have the screen. On our screen we have a hole with crossed wire. This is acting as an object. And then we have the candle, source of light, that will illuminate our object. So the rays that are incident to the lens, they will emerge parallel. And when they emerge parallel, they will strike the mirror. On striking the mirror will reflect them back, such that now the image will be formed on the same plane as the object. So if you find that this image is clearly focused, then it implies that where this one is formed is at F, that is the principal focus. So again, for you to get the focal length, you're supposed to measure the distance between the lens and the screen. Remember, we are saying that any ray that is coming from the object will emerge parallel, and then it will strike the mirror normally. The mirror will reflect them back, and the image will be formed at the principal focus. Therefore, you get the distance of the screen and the lens to be your focal length. We have the third method using a pin and a plane mirror. This one we call it no parallax method, and we have the arrangement as follows. You have the mirror. On top of the mirror we have the lens. Then you have the pin that is attached on a cork. You're supposed to adjust this pin up and down until you find that the image and the pin have no parallax. They just seem to be in the same position or the same line. So to get the best results, we are saying that you tilt the plane mirror so that the tip of the image of the object appears to touch at the same level as the center of the lens. Then for you to get the focal length, you're supposed to measure the distance between the lens and the pin. That way you're able to get the focal length in centimeters. Then we have the third method. We have using the lens formula. I want us to consider this image of this object. We have an object OB, that is the height. It is forming an image IM. We have all this ray that is parallel, it's passing through F, and the ray that is passing through the optical center goes undeviated, so that way you're able to locate the image. So let us consider this diagram and see these distances. From where we have P to O, that will give us the object distance, and that object distance we are going to use U. Then from where we have P to I, that will give us the image distance, and that will be V. Then from the diagram you can be able to see that OB and PH are the same, they have the same height. Then PF on both sides gives us the focal length F. So we are going to consider two cases or two triangles. We have this triangle POB and PIM. Those two triangles are similar, and when they are similar, we have that our OB over IM, OB, remember it is the object height and the image height, is equals to object distance over image distance, because they are similar triangles. And object distance is U, image distance is V. Similarly, the triangles PFH and IMF are similar. This is PH over IM is equals to PF over IF. But remember, PF is our focal length we have shown in the diagram. And our IF, for us to get the IF, you need this image distance PI minus F. PF is the focal length. So IF, where we have IF, we can say that it is V minus U. Let us consider this expression here. We have seen that PF over IF, but IF is V minus F. And also we have seen that our PF is the same as OB. So we have OB over IM, this one, is equals to F divided by V minus F. But OB and IM is what? Is U over V. We proceed. So we have U over V is equals to F over V minus F. We cross multiply. You have U multiplied by these terms, V minus F. You get UV minus UF. Then on the other side we have V multiplied by F. You get VF. Then rearranging, we want to be left with UV on this side, so we take UF on this side. It becomes positive. You have UF plus VF. Then if you look closely here, you'll find that F is common. You factor it out. When you factor it out, you are left with U plus V. And on the other side, you have UV. So we can divide through by F. When you divide through by F, you get UV over F is equals to U plus V. After that, we divide by this term, UV, all parts. When you divide it here, it will cancel out. You are left with 1 over F. When you divide it here, U will cancel out. And when you divide it here, V will cancel out. So you are left with 1 over F is equals to 1 over U plus 1 over V. Now, this one is what we call length formula. And it holds for both converging and diverging lenses. We see the relationship between magnification and focal length. We are considering our mirror's formula, our lens formula here. If we multiply with the V both sides, we are going to get V over F is equals to V over U plus V over V. This V over V will cancel out. It will be 1. Then V over U is M. So replacing, you have that V over F is equals to M plus 1. We have just replaced. Then we rearrange so that we start with M. Our M is our magnification. So M is equals to V over F minus 1. And this is now the relationship between the magnification and the focal length. We consider, when we are using the mirror's formula, we consider the real positive convection is adopted. In this way, we say that all distances are measured from the optical center. That is one thing that you're supposed to note. Then number 2, distances of real objects and real images are positive. Whenever you see a positive, know that it is real. For the virtual distances, we use negative sign. Then the focal length of converging lens is positive because it is real, while that of diverging lens is negative. So we are going to use these 3 when we are using this formula in case we want to determine any value, that is either F, U, or V. Then we look at interpretation of graph of lens formula. We have case 1. We are plotting a graph of 1 over V against 1 over U. Remember, in this graph, they will also help us to determine the focal length when we plot. So when you rewrite our lens formula such that we start with 1 over v, you're going to get that it is equals to negative 1 over u plus 1 over f. Remember, we want to get 1 over v on the y-axis and 1 over u on the x-axis. So we are just rearranging our lens formula, and then we equate it to the equation of a straight line. So if we do that, you will find that on the y-axis it is corresponding with 1 over v, on the x-axis is corresponding with 1 over u, which implies that our m, which is the gradient or the slope, is coinciding, or it is corresponding with negative 1. And our c, which is our y-intercept, is coinciding with our 1 over f. So that way the slope is negative 1 and the 1 over v-intercept is 1 over f. Therefore, from the graph you can be able to get f. When you get the intercept, you just need to get the reciprocal, and that value will give you the value of f. Then we look at the second case, where we have a graph of uv against u plus v. So again, we rearrange our mirrors formula, and we start by getting the LCM. The LCM of u and v is uv. So uv divided by u, you get v plus u. And then we rearrange. So we cross multiply. You have uv is equals to u plus v multiplied by f. And because we want to plot a graph of uv against u plus v, we can just equate this to the equation of a straight line, where we are saying that our y is corresponding to uv, our x is corresponding to u plus v, as you can see, u plus v, and our c is corresponding to 0 because we don't have any value here, which implies that our m is our gradient and our y-intercept is equals to 0. That is, the graph is coming from the origin. So that way again, when you get the slope of this, you are able to get the focal length. Then we move to the third case. We are plotting a graph of u against 1 over m. From the lens formula again, we can multiply through by u. You have u over f, then you have u over u, then plus u over v. But this one is 1 over m. It is the reciprocal of the magnification. Then you have u over u, you get 1. So rearranging, you have this. U over f is equals to 1. This has become 1, and this has become 1 over m. But on the y-axis, we want u. On the x-axis, we want 1 over m. So we can rearrange, and then we multiply through by f. So when we rearrange and multiply, you will get that u is equals to f 1 over m plus f. And then this one, you equate it to the equation of a straight line, where we have that on the y, it is corresponding with u. That's clear. Then x is corresponding to 1 over m. So which implies that our m, which is the gradient or the slope, is coinciding or corresponding to f. So which implies when you get the gradient again, you can be able to get the focal length of your lens. Then we continue with another definition of the power of a lens, and this one we say that it is the measure of refractive property of a lens. Mathematically, power of a lens is given by 1 over focal length, and the SI unit is diopters, which is having a symbol of capital D. If you look at this formula, it implies that if you have a lens of short focal length, then it will have the highest power. We can have an example where you are supposed to calculate the power of a converging lens of focal length 20 centimeter. Remember, 20 centimeter must be in meters. So you convert first, and then you apply it in the formula, where you'll get that power is equals to 1 over 0.2 meters, which is plus 5d. Remember, we insist that for the converging lens, the focal length is positive. It is positive. If we are calculating for the concave, we could consider now to be a negative. Then we proceed to the assignment. In this assignment, you are supposed to plot a graph. Make sure that you use appropriate scale. and get the value that is given here. This will help you to practice, especially on the questions that come on the practical, because when you are able to draw a good graph, you can score much in practical. Thank you, and let us meet in our next lesson.